Welcome to the antennas and wave propagation lecture series. So in this video I am going to explain about the fundamental parameters of antenna. My name is Anusha, Assistant Professor in the Department of Electronics and Communication Engineering, B.V. Raju Institute of Technology, Narsapur. In continuation with the introduction lecture series of antennas and wave propagation, in this video we are going to discuss about some fundamental parameters of antenna and what are the basic parameters associated with this antenna. So generally by that antenna always we are measuring that antenna can be used as either transducer or it can be used as an impedance matching purpose also. Now if for example if antenna is used as a transducer, the antenna will radiate the waves from transmitter to receiver, or if you are using it as a receiver, it will receive the energy, EM energy from transmitter. So in this one, way to represent that radiation. So and that one VAR parameter came into existence. So that is nothing but a radiation pattern. Then the second parameter, if the radiation pattern is represented on paper, then we are calling it as a beam area. Then the next parameter is beam area, and the next parameter is radiation intensity, and the next one is a beam efficiency, and the next one is a directivity and gain, resolution, antenna aperture, effective height, antenna temperature, front to back ratio. These are all the fundamental parameters of the antenna. Let us discuss one by one individually. Then what is the radiation pattern? Simply the radiation patterns are a dramatical representation of the distribution of radiated energy into space. Let us say if antenna can be considered as a transmitter, if it transmits some energy into free space, then we need to represent on a either it could be in picture form or it could that I won't say it could be a diametrical form, so that we can say the radiation pattern is nothing but the diagrammatical representation of the what is the radiation coming out from the antenna. So the radiated energy into space. So it is as a function of direction. So the power when radiated from the antenna has its effect in the near field and far field region. So simply we can say that graphically the radiation can be plotted as a function of angular positions and radial distance from the antenna. So the mathematical function of the radiation properties of the antenna can be represented as a function of spherical coordinate system. That is nothing but the electric field will be mentioned as E of theta comma pi, and the magnetic field can be represented in H of theta comma pi. So here this is nothing but the E-plane pattern. So this is the E-plane pattern, that is we can say that this is electric field pattern of a radiation pattern. The second one is a magnetic field pattern of the radiation pattern. In simple words, from all this definition we can say that radiation pattern is nothing but the graphical representation of the radiation. So these can be represented. Generally these radiation patterns are divided into two types. First one is field strength patterns, and the second one is power field pattern. So here field strength pattern we can say that this is a so here purely whatever electric field, magnetic field all can be dealt in field strength pattern. The second one is a normalized power field pattern. So here for that normalized power pattern, so that can be written as f of theta comma pi is equal to, so E of theta comma pi by, so the electric field maximum direction, where E theta of max is nothing but the electric field maximum direction. This is the expression for normalized field pattern. Then the power pattern is equal to P of theta comma pi is equal to this f of theta comma pi whole square. So this can be represented in dBs. So if that radiation pattern is represented in three-dimensional coordinate system, so this is the view. And if it is represented in polar coordinate system, this is the view, and this will be the three-dimensional view of the radiation pattern. So here this radiation pattern, let us consider it as a lobe shape. If that radiation pattern is considered it as a, for example, let us say, for example, if I place the source or the antenna placed in three-dimensional coordinate system here, so if that the antenna, any practical antenna doesn't radiate equally in all direction. Let us assume that if the antenna radiated the maximum direction towards to this plane, let us consider it as a major lobe. This is nothing but the major lobe direction, and apart from this one, other directions also we have a radiation. The tall can be called as side lobes. Now this is called as lobe. That means the radiation pattern is represented on any graph or any paper that can be drawn like a lobes. Now, so this is the shape what I explained to you. So if, for example, the radiation pattern is represented like a lobe, so let us say this is the maximum lobe. So here the definition for the maximum lobe is the maximum radiation is nothing but the maximum lobe direction. Other than this maximum lobe, all can be called as side lobes. If exactly back to the maximum lobe, that can be called as back lobe. So from this pattern, from this lobe structure, then we are going to define two words. One is half power beam width. If you draw the lines, that means, so here the half power beam width means is the angular beam width between the half of the maximum lobe direction. Let us say if you draw the representing the patterns like this, it should touch this main lobe. So here the power is exactly half of the maximum radiation. So that only we are mentioning it as a half power beam width. So simply it is an angular width. So in for that only, instead of calling it as a bandwidth, it could be called as half power beam width. Now the next definition from this lobe structure is Fresnel's beam width. That means if we observe this radiation pattern direction, for this part we have a radiation, and except this major lobe, other parts we have the radiation. We are representing this as a side lobes or minor lobes we can call. So except this radiation, in other radiation, see exact beside of the major lobe, we have a some part. So here we don't have any radiation. So it doesn't covered with the any lobe. So exactly beside of the major lobe, if you draw like this, so then the angular width between these nulls. So that means there is no radiation. Simply we can represent with the null. So the angular width between these nulls. So exactly those nulls can be represented beside of the major lobe only, sides of the major lobe only. So this angular width will be represented as a full null beam width between first nulls. So this is the definition for half power beam width as well as full null or first null's beam width. We can say that can be represented as, in short form, it can be called as FN, BW and half power beam width. See, if you observe this, if you are represented in the here like see in this one, here the red color represented as a major lobe direction, and exact to the this major lobe direction, this blue color represent the exact opposite to the major lobe. This can be called as back lobe. Other than these two lobes, all can be called as minor lobes or side lobes. So here from these lobes we can define one more word, one more definition, that is front to back ratio. So here the front to back ratio is the ratio of major lobe direction to the back lobe. So this is the concept of radiation pattern. Now these radiation pattern depends on the antenna radiation. Radiation patterns will be divided into different types. The first one is isotopic radiation pattern. So let us say isotropic radiation patterns means, let us consider the three-dimensional coordinate system. Let us consider here isotropic means isotropic radiator is nothing but the one reference antenna. This isotropic radiator will radiate equally in all direction. For example, consider this isotropic radiator as a point source. If that isotropic radiator is placed in the origin of this coordinate system, let us say, so if which will radiate equally in all direction. So, the radiation pattern of isotropic antenna is nothing but a sphere. That means, which is radiate equally in all directions. So, this is called as isotropic radiation pattern. That means, this radiator radiates equally in all directions. The isotropic radiation the isotropic radiator radiates equally in all directions. Let us see. The next type of antennas, so directional patterns. So in these directional patterns, let us say here, for example, say if we consider if any practical antenna are directional pattern antennas, so the same that antennas can be radiated in any one direction. So for example, if the antenna is placed here, let us say that antenna could be a directional pattern antenna. If it radiates along to the y direction, then the maximum radiation direction is towards to the y, or else it could be towards to the x, or it could be towards to the z. The maximum radiation direction is either one direction. The other side, there may be a chance of radiation, but all can be called as side loops. That means there is a minimum radiation. So the next radiation pattern is nothing but omnidirectional pattern. Let us say in omnidirectional pattern, simply omnidirectional pattern, we can say that it is along to the plane. The radiation patterns are along to the plane. If we want to consider the radiation is towards x and z plane, if the radiation is towards to x and z plane, then we can represent like this. Here the major lobe directions are towards to z direction and towards to the x direction. This is called as omnidirectional pattern. So depends on the radiation coming out from the antennas. If it radiates equally all direction, then we are representing that is nothing but isotropic radiator, which will radiate equally in all directions. In generally, this isotropic radiator is a always this isotropic radiator we are using it as a reference antenna. And the next pattern is directional pattern. So under this directional pattern, so these antennas can be radiated towards to one direction only, either wherever you are placing the antenna. So the maximum radiation direction is so either on one side. Next, coming to the omnidirectional pattern. So omnidirectional pattern is here the radiation direction is along to the plane. So like here we have seen, so if the radiation is along to the x and z plane, and here the major lobe directions are towards to z and towards to x. That means in omnidirectional, there is no back lobe concept. So there is no back lobe concepts. So these three are the types of radiation patterns. Now coming to the one more important parameter on the antenna is nothing but beam area. It also called as beam solid angle. So simply the beam area or beam solid angle, the representation for this beam area or beam solid angle is MoA. This is the notation for the beam area or beam solid angle. So this can be defined, this beam area or beam solid angle of any antenna can be defined. It is given by the integral of the normalized power pattern over a sphere. So this can be written as it is equal to, so integral of the, why? Because it is over a sphere, for that only here we have written it as a integral of surface integral of 4 pi into So normalized power pattern Pn of theta comma pi and d omega. So here this can be written as integral. So here we have two directions, either theta or pi directions. So pi is equal, we can represent 0 to 2 pi and theta is equal to 0 to pi, and the normalized power pattern is Pn of theta comma pi into sine theta d pi. This is the one definition of beam area. And the next definition, if beam area can be represented in terms of angles, so in terms of half power beam width. So let us say the beam area can be defined in terms of angles. So the beam area of any antenna can be described approximately in terms of the angles. So that is nothing but half power points of the main lobe in the two principal planes. However, previously we have seen that along to the theta and pi direction. So this beam area is equal to the half power points along to the theta direction and as well as half power point along to the pi direction of the main lobe. So that is theta HP into pi HP. And the units of this one is steradians, SR. So this is the definition of beam area. Now where this, here we are representing always this with the d omega. So this is nothing but solid angle, where the d omega is nothing but solid angle. It is expressed in steradians or square degrees. So generally this steradian can be calculated from this one. Let us say, so for this one, here we are going to consider the three-dimensional coordinate system. Let us assume the antenna is placed at the origin of this one. If it radiates to the some point P, so here we want to calculate the beam area. So that is nothing but, this is mho A. So here this mho A can be represented in terms of steradians. So from this one we can calculate the steradians. That means we can say that it is a solid angle. From this one, this d omega is equal to, so we are calling it as a solid angle. It is nothing but sine theta d pi, where dA is nothing but r square into sine theta d pi, where in place of sine theta, if you replace with this d omega, that means with the solid angle, then dA is equal to, we can write it as a, so here we can write dA is equal to, from this one, or so from this one we can write it as a r square d omega. From this one we can say that r square is equal to dA by d omega. And this is the one relation where we have it for area as well as solid angle. Now, the radiation intensity. So here radiation, the next definition of this parameter, fundamental parameter is radiation intensity. The power radiated from antenna per unit solid angle. So this is the definition of radiation intensity. The definition of the radiation intensity is how much of the power radiated from antenna per unit solid angle. So that is nothing but u of theta comma pi. So where u of theta comma pi is nothing but, so u of theta comma pi is nothing but the notation for the radiation intensity. So it is written as power radiated from the antenna. That means now power radiated from antenna per unit solid angle. Per unit solid angle. And in other words, it can be write as P into R square. So this is a definition of radiation intensity. So before going into this radiation intensity, and the same here we have seen this also can be written as P into ds by d omega, where we have seen this r square is equal to, in previously we have seen this r square is equal to dA by d omega in place of this area. So I am considering it as a ds, or else we can write it as a dA by d omega. This is the one more relation between the radiation intensity as well as in terms of solid angle. So here before to discuss in depth about the radiation intensity, we'll see about the radian and steradian words. Simply the radian is nothing but the plane angle. If we consider, let us say if you consider if the antenna radiates, so let us say, so which will radiates like this. So simply if you consider the angle here, this we are always representing with the radian. If it is a three-dimensional, so then we are saying it as a steradian. Simply radian is nothing but the two-dimensional and steradian is nothing but that means solid angle. Steradian is nothing but solid angle. So it is a three-dimensional. So the radian is analog to a triangle, square or circle. But the solid angle, why here especially we are representing this steradian is, so we are considering this radiation in three dimension. We are representing that radiation patterns in a three-dimensional coordinate system. So for that only, so that is analogical to a cone, cube or sphere. So for that only here we are going to consider always the steradian concept. Now, so this is the picture. If for example, let us say the total circle circumference is 2 pi radians and we are going to say that if the arc length is r. So we can say that we can write this radian is equal to, so 2 pi r square by, so r square. Simply from this one we can say that this entire circle is having 2 pi radians. So this is about the radian. Then coming to the steradian, the same if we consider for the steradian. So for that one, this omega is equal to, we can say that it is having this one solid angle. So this steradian is equal to, we can write the total surface area. So the area of this one is, we can write it as a 4 pi r square. So total it is having 4 pi steradians. If it is having a 2 pi radians and it is having 4 pi steradians. So 4 pi into r square. So in place of this 4 pi, if you are going to represent as a, if you are going to represent this with the steradian, so this is omega into r square. So now, then coming to the same radiation intensity concept. So the total power is obtained by integrating the radiation intensity. So here we were defined that radiation intensity is nothing but the power radiated from antenna per unit solid angle. That already we have written U is equal to power per unit solid angle. We were represented with the P into R square. Now, so then how much of the total power obtained from any antenna, if we want to calculate that one, then the total power is obtained from any antenna. So that can be calculating by integrating the radiation intensity. So that they have written it as a P radiated is equal to integrating the radiation intensity, U into and solid angle. Now it can be written as, so pi is equal to 0 to 2 pi and theta is equal to 0 to pi and UV is nothing but U, and in place of this is a radiation intensity, in place of this solid angle we can write it as a sin theta d pi. In another words, this can be written as the P radiated power is equal to integral of the radiation intensity. The another way, if we want to calculate the total radiated power, this is equal to integral of the average radiated power into ds. So this can be written as P average is equal to, this will be written as ds. So where ds is equal to, we have seen previously, so it can be written as theta is equal to 0 to pi and pi is equal to 0 to 2 pi, and in place of ds we can write it as a r square sin theta d pi. Now this will be written as, so this P radiated is equal to P average into r square. So this will be written as integral pi is equal to 0 to 2 pi d pi, we have only, we don't have any pi terms, and into integral theta is equal to 0 to pi sin theta d theta. Now it is writing as P average into r square So this will be written as integral, we have 1 into d pi, so that is the pi, so 2 pi minus 0. So this will be written as 2 pi into integral of theta is equal to 0 to pi sine theta d theta. This can be written as minus cos theta, integral sine theta d theta. It will be written as minus cos theta, and the limits are 0 to pi. Now it will be written as P average r square 2 pi into, now so it is equal to minus cos theta minus of cos pi. So that means cos 180, it is minus 1 minus, so cos 0, that is 1. Now it is equal to P average r square 2 pi into minus 2 minus into plus 4, so that is 4 pi. So it will be written as the radiated power is equal to P average into 4 pi r square. This is the another way to calculate the total radiated power is equal to the average radiated power into 4 pi r square. This is the one way to calculate the radiated power, and these are the graphs. So the radiation, if it is let us say if the radiation intensity is distributed isotropically, so this is the picture of this, if the radiation intensity distributed isotropically. If it is a directional antenna, so for any directional antenna the radiation intensity picture is like that, means towards to any direction, so that I was represented is from any actual antenna. Now this is the way to calculate the total radiated power for any practical antenna. Let us say it as if that antenna is an isotropic source, so the radiation intensity of any isotropic source can be represented as U0 is equal to the radiated power by 4 pi. So generally we can write it as a P radiated by R square, but for the isotropic antenna it can be written as U0 is equal to P radiated by 4 pi. So this is about the parameter of radiation intensity of the antenna. Thanks for watching this series lectures of antenna and wave propagation. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.